In this video, we look at two more uses of integration, specifically using the integral to calculate the arc length of a curve and using the integral to calculate the surface area of a solid of revolution. Okay. So let's start by examining arc length. So the first thing we're going to do is consider the graph of some function y equals f of x over some interval a to b. So that'll look, I don't know, something like this, let's say. And we want to find the length of this curve. So first what we do is we choose a partition, call it P, that will divide our interval AB into n subintervals. With n points given by this, x naught equals a, which has to be less than x1, less than x2, less than so on and so forth, less than xn, which is b. Right? So obviously that's P1, that is Pn. Now, the thing is, these subintervals do not have to be equal length, so we can choose them however we want. So let's say that is P1. Say that is P2. This is some point, call it Pi minus 1. Right, we can call this point Pi, and then again we have Pn, right? And the idea is we now connect these points as straight lines. So what we do is define the point Pi to be, obviously, the ordered pair xi, f of xi. Join the points, call it Pi minus 1 and Pi by a line segment call it Li. Right now, notice then that this total curve, which we shall call L, made up of all the line segments L sub I is called a polygonal. It's called I want to get this right. Polygonal, yes. Polygonal approximation to y equals f of x, right? Well, then the length of L is then the sum of all the lengths of the line segments. Right now, obviously, as the number of subintervals increase, we're going to get a better and better approximation to the actual curve, and hence this sum will give us a better approximation to the true arc length. Right, so if we look at the norm of the partition, represented that way, is defined as the length of the largest subinterval. Notice that as we let the number of subintervals increase to infinity, the norm of the partition is going to decrease to 0. It's going to approach 0. Therefore, what we say is our arc length S is the limit as the norm of the partition approaches 0 of the sum I equals 1 to n length of L sub I. What we want to do is now take a closer look at this. So let's zoom in. On our graph. So let's just look at something like this. Draw points. Let's say this point here represents pi minus 1. And let's say here is pi. Right, then we're going to have our line segment L sub I right there. Now what we do is draw a straight horizontal line from xi minus 1 to xi, and then a straight vertical line up to the point as such. And notice we wind up with a right triangle. Well, let me rewrite L sub I somewhere else. Let's write it up here. So that distance is delta x. This upwards distance here would be the absolute value of f of xi minus f of xi minus 1, wouldn't it? Well, notice now, like I said, we have a right triangle. The length of the line segment, L sub I, is the hypotenuse. Right, so what we're going to have is, by Pythagorean theorem, the length of L sub I squared is equal to this delta x. It should be delta x sub I. Delta x sub I squared plus the absolute value f of x sub I minus f of x sub I minus 1 squared. Right, that obviously means that this length we're interested in is the square root of this delta x sub I squared plus this absolute value squared. What we're going to do now is assume that f prime of x exists and is continuous. Then, by the mean value theorem, there is some value, call it c sub I, in this interval such that f of x sub I minus f of x sub I minus 1 is equal to f prime of c sub I times x sub I minus x sub I minus 1, but that is precisely delta x sub I. So what we now get is this. The length of L sub I is the square root of delta x sub I squared plus, now f prime of c sub I times delta x sub I squared. Notice there's a delta x sub I squared common, so we can factor it out. We get delta x sub I. We don't need an absolute value, right, because delta x sub I is guaranteed to be positive, times the square root of 1 plus f prime of c sub I squared. Thus, the arc length is now the limit as norm of the partition goes to 0. Sum I equals 1 to n of delta x sub I times the square root 1 plus f prime c sub I squared. But that is a Riemann sum. So this limit is actually the integral from a to b, square root of 1 plus f prime of x squared dx. So we now formally state the arc length formula. Right, the assumption we made was we had f prime exists and is continuous over the interval a to b. Then the arc length call it little s, of y equals f of x over this interval is s equals the integral from a to b, square root 1 plus the quantity of f prime of x squared dx. So let's go ahead and calculate the arc length of f of x equals 2x to the 3 halves over 0 to 1. All right. Well, first we need f prime. So that'd be what? 3x to the half. Okay. So our arc length, the integral from 0 to 1, square root of 1 plus 3x to the half squared dx. Right? Well, that's the integral from 0 to 1, square root of 1 plus 9x. This is a simple u substitution. We'll have 1/9 times a half times the quantity of 1 plus 9x to the 3 halves. And that'll be evaluated from x equals 0 to 1. I'm sorry, that's not 1/2. That should be 2/3. Yes. So that's 2 over 27 times, right, 10 to the 3 halves. Minus, now when x is 0, we get 1 to the 3 halves. So that's 2 over 27 times the quantity 10 root 10 minus 1, and that is our arc length. Right, so next, let's calculate arc length of f of x equals x squared over 1 to 3. Again, first we need f prime. That is 2x. So the arc length would be the integral from 1 to 3 of the square root of 1 plus 4x squared dx, right? It's 1 plus 2x all squared. So that leaves us with 1 plus 4x squared. Now what we're going to do is make a substitution. We're going to use the substitution u equals 2x, making du 2dx. So that gives 1/2 times the integral square root of 1 plus u squared du. Right, and well, u's now going to go from what? 2 to 6, isn't it? Now the reason to make that substitution is so I can use an integral table. All right, so specifically for this problem, the one we're looking for, number 68. And so of course that is the integral table that I'm using. So the formula will be 68 from that. That'll give us u over 2 times the square root of 1 plus u squared plus 1 over 2 natural log of u plus square root 1 plus u squared. And of course we want to evaluate that whole thing from 2 to 6. Right, 1/2 6 over 2 is 3. Square root of 37. Right, 1 plus 36. Plus a half log 6 plus square root of 37. Right, then it'll be minus, now I evaluate it again at 2, so it'll be 2 over 2 is 1, so root of 1 plus 4, root 5, plus a half log 2 plus root 5. Simplifying all this out, 1/2 3 square root of 37 minus square root of 5 plus a half log 6 plus root 37 over 2 plus root 5. We can distribute that 1/2 through and we get 3/2 root 37 minus root 5 over 2. What I actually want to do is I'm going to rewrite this first one as 3 root 37 over 2 instead of 3/2. Right, and then plus a quarter log of 6 plus root 37 over 2 plus root 5, and that would be our arc length. All right, now let's calculate the arc length of y equals sine of x over 0 to pi, and we want this accurate to 4 decimal places. Right, now f prime. It would be cosine of x, right? So the arc length would be the integral from 0 to pi, square root of 1 plus cosine squared dx. Well, notice that this is not going to have an analytic solution. So we're going to have to use a numerical approximation. Right? And whenever we need to use a numerical approximation, unless specified otherwise, we will use Simpson's rule. So come over to our calculator. First, I want to set up my Simpson's rule. So I'm going to define a function, delta x, as a function of n, and define that to be b minus a divided by n. Now I'm going to go ahead and define my actual Simpson's function. So Simpson's as a function of n. I'm going to define as 1/3 times delta x of n times, right, now we're going to have f of a plus f of b plus 4 times a sum, right? So menu, calculus, sum, j1 to n over 2, f of a plus 2j minus 1 times delta x of n plus 2 times another sum, j will go again from 1, but this time n over 2 minus 1, f of a plus 2 times j times delta x of n. So now my Simpsons rule set. Now I just need to define my function. So my function is the integrand, which was the square root of 1 plus cosine squared of x. So cosine of x all squared. A was 0. B is pi. Now we just need to start evaluating values of Simpson's rule until we get terms that agree up to 4 decimal places. All right, so Simpsons of 4. And remember, n has to be even for Simpson's rule, so let's look at 6. 8. Something is wrong. I just want to make sure that everything is defined properly. I see. Okay, no. I need to fix this. Notice what wound up happening is I put this sum within the first sum. It's not going to let me do this. So what I'm going to have to do is delete this. No, not that. I want to delete all of this. Okay. Make sure I'm totally out. Okay. Now plus 2 times, let's try this again. All right, so Simpsons of 4. Now let's do 6. That looks better. All right, so they do not agree to 4 decimal places. So let's continue on. 8. They don't agree. 10. They don't agree. 12. There you go, they agree. We get 3.8202 to 4 decimal places. And we used S sub 12 to get 3.8202. We will now look at surface area. what we're going to do is proceed in much the same way as we did for arc length, with one key difference. What we're going to do is we're going to rotate this curve about the x-axis. Oh no, let me try and do it this way instead. Let me scroll all the way back up. Let me see if I can just select this, copy and paste it. Excellent, it lets me do that. Right, so we're rotating about the x-axis. Right, so again, we're assuming f of x is greater than or equal to 0. And we are revolving it about the x-axis. Notice that this is going to result in a solid of revolution. Let's call it R. Now our goal is to determine the surface area of R. What we're going to do is we're going to create another solid of revolution. Call it R star. By revolving our polygonal approximation about the x-axis. In other words, we're rotating the blue around the x-axis. Right, so the result is a surface, R star, that lies very close to R, and whose surface area approximates the surface area of R, which we shall call S, capital S. Now, notice that R star is made up of slanted bands, all right? So what we do is we consider the slanted band corresponding to the interval xi minus 1 to xi. The segment L sub I along the total slanted band, right? Is a segment of the polygonal approximation. Right? Now we already know what the length is. Right? This is our length for some c sub I in our interval. Now, if our delta x sub I is small enough, what we can do is approximate the surface area of this slanted band as the surface area of a cylinder. Of width, length of L sub I, and radius, f of c sub I, now the surface area of a cylinder is 2 pi times the radius times its width. So for our purposes, we're going to have 2 pi times f of c sub I times the square root of 1 plus f prime of c sub I squared times delta x sub I. Let's call that the surface area of cylinder I. Right? Obviously, this means that the total surface area is the sum as I equals 1 to n of all of these individual surface areas. Which is approximately sum I goes from 1 to n, 2 pi times the sum as I goes from 1 to n, f of c sub I times the square root of 1 plus f prime of c sub I squared delta x sub I. Right, now clearly this is a Riemann sum, and so we can now formally state our surface area formula. Right, so we're assuming that f of x is greater than or equal to 0, and that f prime both exists and is continuous on the interval a to b. The surface area S, big S, of the surface obtained by rotating the graph of f about the x-axis obviously for a less than or equal to x less than or equal to b is 2 pi times the integral from a to b f of x times the square root of 1 plus f prime of x squared dx. As an example, we're going to calculate the surface area of a sphere of radius r. Right now, what we can do is we can generate this sphere by rotating this semicircle about the x-axis. So this semicircle is going to have equation y equals the square root of r squared minus x squared. Right, that means that y prime is negative x over the square root of r squared minus x squared. So surface area, 2 pi times the integral from negative r to positive r, square root r squared minus x squared, times the square root of 1 plus x squared over r squared minus x squared. Now, let's simplify this. We're going to have the square root r squared minus x squared times square root of simply r squared over r squared minus x squared. Continue to simplify this. We're going to get 2 pi r times the integral from negative r to positive r. And what are we left with? Just simply dx. So we get 2 pi r times the length of this interval, which is twice r. And so we get a surface area of 4 pi r squared. And if you recall from geometry, that is the formula for the surface area of a sphere of radius r from geometry.